Hi students, this is Satish Kumar. In this video lecture, I'm going to tell you the expression for the absolute potential. In the last lectures, we have seen the potential difference due to a point charge, and we have got that as, we know that the potential difference, we have denoted it by VAB, which is equal to Q by 4 pi epsilon into 1 by RA minus 1 by RB. Here it's a potential difference. We know that this is also indicated by VA minus VB. It is the potential at point A minus potential at point B. But here, what is the meaning of absolute potential? Absolute potential here means there is a single potential, either the potential at point A or the potential at point B. So which one? Here we are going to get it. If you observe this, Q by 4 pi epsilon into 1 by RA minus 1 by RB, we are actually moving a test charge Qt, which is equal to 1 coulomb from a point B to a point B, to a point A. And this much amount of work to move, work done to move a 1 coulomb of charge from B to A is called as potential difference. Now the point is, we cannot make this VA to become 0 because VAB will become minus B if VA is made 0. So the option that we have left is VB should be made 0, and this is only possible. We cannot make VA to 0. How can we make this VB to 0? So VB is from the expression which is clear that Q by 4 pi epsilon RB. How can we make this VB to 0? We cannot make Q 0 because Q should be there to generate the to create the electric field. So we cannot make that to 0. So to make this VB 0, the only option is we have to make this RB, which is equal to infinite. Now what we have to do is we have to move this point from the location RB to a location where the potential is 0, and this is a point which is at infinite, where the potential at that infinite point is taken as 0, and this we call it as reference point where the potential is 0. This is called as reference point. Now the test charge Qt, which is equal to 1 coulomb, is here. This is Qt, which is equal to 1 coulomb of test charge. Now you have to move this test charge from infinite to a location which is A. Okay, so this is the location to which we are moving, and for that absolutely we require some amount of work, and that amount of work to move this 1 coulomb of charge from infinite where the potential is 0 to a point A is called as absolute potential. So here everything is work done, starting from the expression of work done, potential difference and absolute potential, all are work done only. Okay, so this absolute potential here is defined as the work done or amount of work done to move a 1 coulomb of test charge from infinite to a location A is called as absolute potential. Okay, that's what we have to write here. So definition of absolute potential is, it is the work done to move 1 coulomb test charge 1 coulomb test charge from infinite to a given point. That given point here is A, is absolute potential. Okay, so this is the definition of absolute potential. Now we'll try to make the expression VAB, which is equal to Q by 4 pi epsilon into 1 by RA minus 1 by RB. So what we should now do is you have to make RB is equal to infinite, and VAB obviously is going to become simply VA, because at B point we are going to have the potential 0. Therefore, if you substitute RB is equal to infinite, that VAB will become simply VA, that is Q by 4 pi epsilon into 1 by RA minus 1 by infinite is 0. Therefore, VA, it is the potential at point A, will be Q by 4 pi epsilon RA, and the units are here volts. Volts, right? So this is an expression for the absolute potential at point A, because you are moving finally the test charge to a location A, and we are also getting the potential at that particular point. Wherever you move the point, which is a 1 coulomb of test charge, and that is the potential where we are actually finding out, right? So in general we can remove that A point. That point can be anything. So V is simply equal to Q by 4 pi epsilon r. A is not required, 4 pi epsilon r, simply these many volts. Okay, so here V is directly proportional to charge, and V is inversely proportional to the distance. As R increases, potential is going to decrease. Okay, so this is a very, very important expression to find out the potential due to a point charge. This is nothing but the potential due to a point charge. There is no square, and here V is also called scalar potential, scalar electric potential, which is a scalar quantity. It's not a vector because there is no direction, which has only magnitude. Now we will extend this to another very important expression that will get it. So potential at a point due to n number of charges. N number of charges. This is similar to the force on a single point, single charge due to n number of charges, and E at a point due to n number of charges. In the same way, we have to do this potential also, right? So at this point, I want to find out the potential. Let us call this is some point P, and I want these are the charges which I'll be taking like this. There are n number of charges like this. So what I'll be taking, this is Q1, this is Q2, Q3, Q4, so on, Qn. So to find out the potential at this point, Q will be creating some field around this, Q2 will be creating some field, Q3, Q4, so on, Qn. Because these many charges are creating a very high field, the potential at this point is also very high. Okay, so now let us try to join these points, right? Join this, join this, and also join the nth charge. Now Q1, due to this Q1, I am finding out the potential at this point. Let us call that potential is V1. Due to Q2, I am finding out the potential. Let us call that is V2, and similarly V3, V4, so on. This is Vn. Now the point is there is only one thing here, because there is no direction which is required here. the distance between this point charge and the point where you are measuring the potential is, let's say, R1, and this is R2, R3, R4, and so on, Rn. Now, I want the total potential at this point. The total potential at this point will be calculated by using superposition principle. So here we have to go for superposition principle. What the superposition principle is stating. Superposition principle states that the total potential at this point, let us call that is Vp, okay, potential at point P, is the potentials, algebraic sum of the potentials due to individual charges. So the total potential at point P is equal to algebraic sum of the potentials due to individual charges. So we can say that is summation of the potentials due to individual charges. Let us call that is I, where I is equal to 1 to n here. So this is expanded as Vp will be equal to potential due to charge Q1 is V1, potential due to charge Q2 is V2, potential due to charge Q3 is V3, and so on, Vn. But what is Vn? It is the potential due to this charge Q1 at point P. And how much is that? Q1 by 4 pi epsilon R1. There is no vector here. And what is V2? Which is Q2 by 4 pi epsilon R2 plus so on. What is Qn is? Qn by 4 pi epsilon Rn. That's it. This is potential at a point P due to n number of charges. You will be getting the problems on this. You have to find out the potential at this point P individually, and you just need to add it to get the total potential, right? Now, there is another topic that we have to discuss. Okay, with this we can close this particular work done concept. And one more point or topic that we have to discuss here is equipotential surfaces. What are these equipotential surfaces? The name itself is saying that the potential on that surface is equal. Okay, let us take a surface and we'll try to see whether that is possible or not. Let us take this is a surface, plain surface, open surface. On this, let us try to have different points like this. But assume this is in a rectangular coordinate system where every point is having different coordinates, right? Now, the potential, let's say here is V1, here is V2, here is V3, V4, V5, and V6. Generally, as we know from the expression, we will be having, if it is dependent on charge, the expression is q by 4 pi epsilon r. Generally, that we will be having an expression something like this: x square plus y square plus z square is in terms of rectangular coordinates. So, if you take the point is, let's say 1 1 1, and this point is, let's say 1 1 2, this is 1 2 3, and so on. So if you substitute these points, suppose if you want at V1, V1 may be something like 3 volts, and V2 is something like 1 square plus 1 square plus 4 square, 2 square is 4 plus 2, 6 volts, and everywhere that V3 is also having a different value, right? So now the point is the potential here, potential here, potential here will be different. But there is no way you will be generally getting the potential is same when you take a plane surface which is in a rectangular coordinate system and you try to check it. Okay, but why this particular topic equipotential surfaces has come into the picture? So here we can define this as this kind of surfaces generally will not exist in real, so we can only think that this is we can say an imaginary surface. Okay, but I'll try to give you the equipotential surfaces, how they will be existing in real, right? But let us try to first define what is this equipotential surfaces. So as it is generally not possible in real, we can call it is an imaginary surface. So the equipotential surface is an imaginary surface, imaginary surface in which the potential everywhere is same, because equipotential itself indicates the potential everywhere is same. So this is the definition of equipotential surface. It is an imaginary surface in which the potential everywhere is same. Imaginary or hypothetical or fictitious surface, anything you can call it. You can also call it as fictitious surface, right? Now, what are the important points that we have to discuss in this equipotential surfaces? If you observe, the potential, let's say here is V1 and here is V2, right? And I am saying these potentials are, let's say, same. V1 is equal to V2. What is going to happen? That means this is equal to, let's say, V, and this is also equal to, let's say, V, and this is also equal to, let's say, V. And if this is the potential V and this is also potential V, what is the potential difference between these 2 points? VA minus VB or V1 minus V2, that is V minus V is equal to 0. So the first point that we have to write in equipotential surfaces is the potential difference, the potential difference between any 2 points, any 2 points in an equipotential surface is same. In an equipotential surface is same. Sorry, is 0. Is 0. Right. This is the first point. Next, suppose as the potential here is same, suppose if I want to move a 1 coulomb of charge from this point to this point or this point to this point, as the potential everywhere same, the work done is based on the potential difference. If the potential difference itself is the same and 0, and the work done will become 0. That means to move a 1 coulomb of charge from one point to any point in an equipotential surface, the work done required is 0. That is second point that you have to write. The work done required to move 1 coulomb test charge or any charge in equipotential surface. Equipotential surface from one point to another point is 0. Is 0. These are the two very important points that we have to write for the case of equipotential surfaces. Now there is a third and most important point. Suppose if you see this is an equipotential surface, you can also divide that equipotential surface into equipotential lines like this. If you write them in very closer like this, they will become equipotential lines. Equipotential lines, right? These are equipotential lines, let's say, right? Now, if you assume these are electric field lines, electric field is, let's say, in this direction. We have seen in work done that the fifth point that I discussed in work done was, if you try to move any point perpendicular to the electric field, the work done required is 0. So here what are the lines which are perpendicular to this electric field? We have the electric equipotential lines, right? So in this equipotential lines, already we have seen that if you try to move a 1 coulomb of charge from one point to another point in this equipotential lines like this, the work done required is 0. Not only vertically, horizontally is also 0. Okay, but here I will be considering these are the equipotential lines, okay, and these are the electric field lines, right? So if you try to move any charge perpendicular to this electric field, and in perpendicular here you have the equipotential line. So what we can conclude here is the equipotential lines are surfaces and electric field lines both are absolutely perpendicular to each other. This is one very important point that we have to write in equipotential surfaces. The equipotential lines, the equipotential lines and electric field lines, electric field lines are perpendicular to each other. Perpendicular to each other. Now let us see one example of this equipotential surface. Example of equipotential surface. I said these equipotential surfaces generally will not exist, but how they will exist, we'll try to see now. This is a point charge. This is a point charge, and I'll be taking an electric field around this. Right? This is an electric field around this. And the field lines will always be like this, as I have mentioned. And if you observe, if this is an electric field, the distance from this point to any point on this surface will be same. Let us call this is R1, and this is also R1, this is also R1, this is also R1. So what is your potential at this particular point? Let's say V1. As we know, V1 is equal to Q1 by, let us, or Q by 4 pi epsilon R1. Okay, so this is the potential. See, this potential V1 is only depending on charge and R1. So here charge is same, we are not changing it, and distance everywhere is same. So the potential here is also V1, here is also V1, here is also V1. It's not a circle, it's a basically a sphere. So if you assume this is a three-dimensional thing, so even if you take a R coming out of the board which is at a distance of r, and at that particular point also you will be getting you will be getting the potential which is same. So this is, if you assume it as a sphere, the potential here is also, which is at a distance of r1, here is also it is v1, here is also it is v1, because the distance is same. That means this kind of surface where the potential everywhere is same is called as an equipotential surface. So the surface around a point charge is generally called as equipotential surface. But you just don't get a single surface here, you will be getting concentric spheres. Okay, you will be getting concentric spheres here. It's not circle, sorry, it's a sphere, you will be getting it. And if you take one more sphere, okay, so if you take like this, and the distance from here to here is r2, and the distance from here to here is also R2, and the value here will be V2, and the value here will be V2. So this is another equipotential surface. Similarly, we can have n number of surfaces which will be getting like this. Okay, this is another surface which will be getting like this. We'll be getting n number of surfaces will be getting like this. Okay, so these are all called concentric spheres, not circles. These are all spheres which we will be getting, which we call them as concentric spheres, right? So these are all the examples of equipotential surfaces. Not only around a point charge, even if you have a line charge also, if you distribute charge on this, you will be getting concentric, sorry, coaxial cylinders. You will be getting coaxial cylinders on which the potential is absolutely same. So you will be getting another cylindrical structure like this, and you will be getting the potential on this is also same, right? So this is about around line charge. Similarly, if you take a infinite sheet of charge kind of thing and charge is distributed on it, and if you take a surface which is exactly above a particular distance, the potential on this entire surface will also be say like this. You can have n number of surfaces above and below this particular equipotential surface, and you will be getting the potential everywhere same. So these are all the examples of equipotential surfaces. Thank you very much. And with this class, we have almost completed the part of work done. So because work done is completely a link, okay, we start with work done and its expression, properties of work done, potential difference from the work done expression, potential difference due to a point charge, absolute potential, and this equipotential surfaces. This everything is a set, we can say, right? Thank you. If you like my video lecture, please subscribe my channel. Thank you very much.